Okay, hello. I see Devin. Can you hear me, Devin? Okay, hello. Okay, good. I had to replace the link in the Canvas because I accidentally stopped streaming on accident, so I had to replace it with a new link. I saw that a bunch of people were already logged on, but it looks like people are finding their way here. So I'm going to get started with lecture today. Today, in basic electricity, we're going to talk about resistors, resistor ratings, variable resistors, resistance and resistivity, electrical power calculations, power in series and in parallel. Okay, so hang on, let me log in here. I like to log in to make sure that everything is running, that you guys can see everything I can see on the screen. So I'm going to log into my YouTube on my phone. Okay, so I think I have everything set up correctly, so I'm going to continue with the slides. Okay, so again, today we're gonna be talking about resistors, resistor ratings, variable resistors, resistance and resistivity, electrical power calculations, power in series and in parallel. First, we'll talk about resistors. So what is a resistor? Resistor is an electronic component which have specific and never changing resistance. They limit the flow of electrons through a circuit. These are considered passive components. They consume power, but they can't create it. They can't create it or generate it. This is a flow chart of certain types of resistors. So we have resistors that are linear and nonlinear. With our nonlinear resistors, those would be considered our thermistors. LDRs are light-dependent resistors, photoresistors, and varistors. And we'll get into some of those. We have our linear resistors, which can be a fixed type or a variable type. Our variable resistors being wire wound, potentiometers, trimmers, and our fixed type resistors being carbon composition, thin film, thick film, and wire wound. Here's a couple different types of resistors. We have through-hole resistors here and surface mount resistors. These type of resistors we're not going to deal with in this class very much. These are used in circuit boards, and we don't tear down the components enough to get to those resistors. So we'll be dealing mostly with through-hole resistors. If you guys have any questions, or if I'm going too fast in the slides, just type in the chat and let me know. So we're going to go through a lot of different types of resistors. Here we have a wire wound resistor. There's a diagram there for you describing how a wire wound resistor is made up. It has a metal core, so this is a picture of it, a through-hole resistor. It has a metal core with resistive wire wound around it. We have our carbon composition resistor. We have our color bands, which we will get into. But the makeup of this resistor is it's a through-hole resistor. It has the lead running through it on either side, and it is made up of an outer plastic case with carbon composition clay internally. We have our carbon film resistor. This looks similar to the wire wound resistor, but it has a different makeup internally. You can see it has end caps. It has a carbon film wound around it rather than a resistive wire, and a ceramic substrate internally. And this is a picture of what is called foil resistors. We're not going to deal with foil resistors very much. I just want you guys to know that there are all of these different types of resistors. We have metal film resistors, and this is another diagram explaining the internal makeup of those. The difference being, if you can see at number 4, we have internally metal film, whereas these are all just different internal makeups of resistors. We had the carbon composition with the internal makeup. We had the metal film. We have metal film. We have metal oxide film resistors. So very similar to one of the previous images, but this film is metal oxide. So just different materials that can make up these resistors. This is an image of metal glaze resistors. Okay, some resistor symbols that you will see in schematics. The formatting here got a little messed up, but this square looking schematic symbol is the symbol for a resistor internationally. More specifically, it's the European symbol. So what you're going to see when we're dealing with schematics is this symbol that looks like a line oscillating up and down. That's going to be our American resistors. Okay, we're going to get into resistor ratings, how these resistors are rated mathematically. Resistor ratings go by color bands. We'll talk about color decoding and calculating resistor ratings. So resistor color codes. So I'm sure you saw on some of those images there, they have a few bands with different colors. So those bands stand for something mathematically. First of all, being the first color band indicates a digit value, single whole number digit value. The second color band is the same. It indicates another digit value, a whole number digit value. A third color band indicates a weight value. So this color band is what's called your multiplier. And you'll see this in a chart that I have, but the third color band multiplies the first two significant digits by a power of 10. And there's a chart for what power of 10 those color bands go by. And then the final color band indicates a tolerance of your resistor. So here's your color code table. Okay, so you have all of your bands on your resistor, and if you have a black band first as your first band, what column you're going to use is the digit column, because your first and second bands are always going to stand for your whole number digits. So if you have a black band first, your digit's going to be 0. If you have a brown band second, your digits are going to be 0, 1. And say you have a red band third, your multiplier is going to be 10 to the second power. If you have a red band last, then you're going to have a tolerance of plus or minus 2%. And then we go through how to multiply this equation out. I'm just checking the video here. For some reason, my thing looks like it disconnected. I don't know if you guys could tell that, but anyway, I'll keep going. It looks like it's still recording. I see a question here. Can you have a gold? Hang on. You have a gold or? Can't see the whole question. Can you have a gold or silver first band followed by a single digit band? No, you can't. Good question. You'll never see that because that's just not how the calculations work. So the only time, I'm going to go back to the table here. So this table, you see we have gold, silver, and none. So the only time that you can have gold and silver is as your multiplier band or your tolerance band. You will never have gold and silver as your single digit whole number band. That's just how it works. Which is good, because it would be confusing if you could have it as a single digit band as well. So you will never have a gold or silver band first. You will always have a different color. If you have a gold or silver band at all, you will always see it as one of your last two color bands. So, good question. Okay. So this is a diagram, kind of an example of a resistor value calculation. And we will go through this. I have another example and I think a video. So it is telling you, this diagram is telling you here different resistor color band values that you could have. Okay, so I think that in this diagram the red and the yellow kind of got switched because of where the arrows are pointing. I think that the red actually, for some reason, this diagram thinks it's yellow, and the yellow actually thinks it's red. But there's more slides to kind of keep this straight. So it's just showing you, here you're going to have your first band. Let's say it's yellow. In this chart, it's saying yellow single digit whole number stands for 4. If you had green, it would be 5. If you had brown, it would be 1. If you had orange, it would be 3. So it's giving you all these different examples of what that would look like with different color bands, and just showing you your first color band would be in this row, your second color band would be in this row, your third color band, your multiplier would be, so you're going to have 10 to the second power, which would be 100, and then